Greetings, everybody, and this is back to Fundamentals of Quantum Computing. I'm Daniel Sable. I'll be your instructor, and we're going to be looking at Shor's algorithm. Um, Shor's algorithm is a little bit more heavy in mathematics, which we will see, but 1994, uh, at Bell Labs, an American mathematician named Peter Shor developed an algorithm to factorize a large number into its prime factors. This is known as Shor's algorithm. So here's the mathematical basis. Suppose n is a product of primes p and q. If an integer a is less than n, it's not divisible by p or q, the sequence a mod n a squared mod n to the power of a cubed repeats with the period that divides p minus 1 times q minus 1. Very confusing. In other words, if we consider the function f of x, which equals a to the raised to the power of x mod n, then its period is the smallest positive integer p, for which f of x plus p equals f of x, which is equal to or less than a raised to the power of x plus p, which is equal to a raised to the power of x mod n. It's a little bit confusing, or could be very confusing. So basically what he was doing was he was looking for the prime factors of numbers. And what does that have to do with anything? Well, our regular computer cannot find very large numbers or prime factors. Prime factors are big with RSA, with hacking and so forth, and we'll see this in a moment. This was a five-step algorithm that Shor came up with, and you're going to see on the computer what I was talking about with the mathematics as we kind of get into this a little bit. So let's kind of break it down a little bit. So if by trying random values of x, it is possible to get divisors of p1 times q1 and multiply them to compute p minus 1 times q minus 1. If the product is known, p and q can be determined. If p and q are very large primes, the period of repeat may be too large for a classical computer to compute, but not for a quantum one. So why is Shor's algorithm, and why is this so important? So on a quantum computer, Shor's algorithm can factor a very large integer n into its prime factors in a time that is a polynomial of log n. Remember in one of my last videos that I was talking about the RSA system, and this is widely used in security. A regular computer cannot factor these large numbers, whereby Shor's algorithm will put RSA basically out of business. So here's how it works. Okay, so this is the first step. So you're going to choose an integer m, which is greater than n, such as GCD, and that's greatest common divisor. And m and n equals 1. Factoring, let's say 21, I choose the number 13, okay? I then pass it on, and I proceed to step 2, which is passing it on to step 2. This is the most important step right here, is what we're looking at. This is using a quantum computer. This basically is to find the period of the sequence m mod n, m squared mod n, m cubed mod n. Okay, this is only the state that requires a quantum computer. So first, the initial state of the system is created to skew the latest power of 2 greater than 2n, or 2 to the power of n squared. This is q, which is usually determined how many qubits it will need for the number 21. So q will equal 1024. The initial state will then consist of a number 0 through 1000, 23 in the number one register, and followed by a 0 in the second. So a copy of M is added to register 2 and raised it to the power of the corresponding register 1 mod n. The next step is to measure the second register and observe its state. Each base state is equally likely to be be measured. This measurement projects the original state into a subspace filled with other base states that share the same observed value, and the factoring of 21 that comes to the state of 13, which is observed. The discrete Fourier transform, which is what the whole process is about, is applied to the first register, and then the next register 1 is measured again due to the discrete Fourier transform. The observed probability of state C is concentrated around the values such that C over Q is approximately equal to D over the period where n is an integer. In register 1, it is observed to be in the state of 253. So if we take C over Q and use the continued fraction conversions to approximate D over R, at certain intervals, once a fraction is found whose denominator is greater than n, the system can look at the denominator of the previous fraction to find a factor of the sequence period. Okay. These numbers are tested by substituting them into the congruence m to the power of the multiple mod n until a congruence equals 1. Luckily, 2 happens to be congruent to 1 as has found its period. Okay, so let's go into step 3 of the algorithm. So step 3 basically says that it is possibly one of the toughest to determine because we have to determine if the period is even or odd. If it's odd, the process starts over by picking a new number. Otherwise, the machine passes P into the next step. The period was 2, which is even, so it's able to pass the number into the next step. So we're going to move forward here. So we're going into step 4. I apologize. Step 4 basically is the congruence, basically solved by m raised to the power of the period divided by 2 plus 1 mod n. If the result is 0, the process starts over by picking a new number. Otherwise, the number gets passed on to the next step, which is passing the number 13 squared divided by 2 plus 1 equals 14 mod 21. And this is congruent, so it passes on to step 5. Step 5 uses the Euclidean algorithm to calculate the greatest common divisor between m to the power of p divided by 2 plus 1, which is a non-zero module n which must be a factor of n that calculates the greatest common divisor of 12 and 21. Okay? Because those were the numbers that we chose. To B3, which is a factor of 21. Basically, this is the entire Shor process or algorithm, and we'll see here the conclusion. The task that of factoring an odd positive integer n reduces to the following problem. So there it is. We're factoring n to n, and we're going to find the period p of f. And that was quite difficult in terms of mathematics, and quite difficult in terms of going through the numbers. But long story short, what it is Peter Shor came up with this algorithm that factors numbers that become great in size. And a quantum computer can do that, whereas a regular computer cannot. And when we're able to use these large factorizations, we'll be able to do a number of things like crack passwords and do many other things with the quantum computer. So this is another video in our lesson. Hopefully it wasn't too confusing and it wasn't too much going on. But if you look through it again and you listen to kind of what I say, you will see where it all takes place.